Here we go. So, welcome to our first Focus on a Feature webinar. And I'm going to be talking today about working with graphs in IGB. Most people in the audience have worked with IGB, but I am going to start a little bit from scratch just so that anybody watching this can catch right up with us. So the first step is opening a graph in IGB. As per normal, you can open any file either from a URL or going through the normal file tree. But the graphs I'm going to work with today actually come from Arabidopsis thaliana. That is the organism that the Lorraine lab works on, and so that's what we have a lot of data on. As you can see, clicking that front picture will immediately take you to the latest version of the genome, and it will load all of the annotations for chromosome 1. My preference, because I like to increase the area I have to look at things, I prefer to make both my plus and minus strand into a single location. And over here in the available data section is where I'm going to be getting some of the graphs. I'm going to be opening the pollen quick loads service, and I'm opening RNA-seq data. When we do our RNA-seq, we separate the single mapping reads, that is, reads that only have a single time that they map into the genome, from the multi-mappers, that is, the reads that can map to 2 or more places. Hang on 1 second. Okay, so in this file tree, I can go down here to graphs, and I'm going to click open the 3 graphs that I want to see. And they show up in the track name table, and they form the placeholder tracks up here. But rather than try to load an entire chromosome worth of data, I am going to go to a region that we're interested in. This is the gene I'm starting our demonstration with. So I'm going to double click on it, and we're going to jump here. And then I'm going to open it up to a slightly larger region. My preference for navigating is to use the grab hand, which is a click and drag. Center up on some of the data here. All right, that looks like a good chunk. And to visualize these graphs, now that I'm zoomed into this region, now I'm going to ask to load data. And over here, I'm going to go back to the data access panel. As you can see, our data has loaded in. Another way to actually generate graphs in IGB is we can actually create a graph directly from the RNA-seq data. Again, I'm going to load the single mappers, but this time I'm going to directly load the reads. Again, I open them by clicking on them. They appear in the table, we get the empty track, and I load data. With RNA-seq, you can have very, very large stacks of data. IGB initially limits it to 10 high and then a summary row. But if I use the Optimize button to give it permission to show me all of the reads, you can see that some genes have incredibly tall stacks and others very little, but no matter what, it forces the data out of the way. So we use these coverage graphs, which we call depth graphs, because it measures the depth, how many of these alignments are stacked at one genomic location, and renders it into a number. And graphs are much more flexible than these very large stacks of alignments. So I click on the first track, and then I use Shift and click to select the second track. Go to the Annotation tab, and here I use the operation called depth, which will draw for me a depth graph, and I apply it. And once IGB has drawn for me those two tracks, we go back, we will in a moment. There we go. We go back to the data access. I no longer need to see these two tracks, and yet I don't want to just delete them. So what I do is I click on the eye icon and hide them. And now we have all of that information rendered into graph outline, into a graphical format. So now we have coverage graphs that we've loaded, either that were made from outside or that we made inside of IGB. And you can see that little yellow IGB track mark indicating that this is a track that was created by IGB, and if you want to keep the data, you'll need to save it. So right off the bat, I'm going to do a few things to make this easier to work with. I don't like having huge long names when I'm doing my analysis. So I'm going to click on the name in the track, and I'm going to change it to something short. And I'm going to do that for everything real quick. Those don't matter, they're not showing. So right off the bat, we've made it a lot easier to keep track of what we're looking at. The next thing I'm going to do is I'm going to come to the Graph tab. I'm going to select all, and I'm going to use the Style element to change this to a more comfortable way to look. My personal preference is I prefer a white background. So I select them all and change them to a white background. Now, these are different experiments, so this control goes with cold and was quite possibly done at a different time and in a different way than the controls for the pollen. But when I look at data, I tend to want to put my controls together. So I've identified what kind of control it is, but as you can see, we can once again move tracks around, move things to different areas to make our analysis a little easier. The other thing I prefer, again, personal preference, I tend to like the stair-step presentation because although these look solid, they're set to the min-max mean. So if we zoom in, what it shows you is the distinct units by width that each one of these things cover. And stair-step will fill that in for me solidly. You can also use line, bar, dot, heat map, whatever actually makes it easier for you to see the information in your data. Now, right off the bat, it's incredibly clear that something is going on here in pollen that is not going on in any other one of the tracks. Over here, it looks like there is quite an overexpression of cold, and here, these all look equivalent. But I'd like to draw your attention to the y-axes. The problem with that quick assessment is if you look, the scale of cold goes up to, let's say, 575. The control is over 800. Both of the pollen, the controls for pollen are 1.5K to 2K, and pollen's at 4K. So right off the bat, these are not on the same scale, and that's something you need to be aware of. Now, we can easily fix that in some ways. So I can select all of my tracks, choose the value rather than by percentile, and I can choose the highest maximum for the Y to set them all to the same scale. So here I'm going to put in 4200. And now, all of these y-axes are on the same scale, all of these expressions are represented at the same scale, and unquestionably, we have something of a pollen-specific gene here. And yet, all of the rest of the genes we look at have almost no expression. Well, they appear to only have almost no expression. Again, we're only looking at a gene that has at least 4,000 reads stacked up at the highest point. So that may not be the most practical number. So I'm going to select them all, and this time I'm going to change the scale to, let's say, 2,000. Much better. We now see that this gene is better represented by this y-axis scale. And you can see, as opposed to the first time we saw it, it looks like cold might actually suppress this gene rather than allow it to be expressed at equivalent values. And again, I can further reduce the number to 500. And here we can see this gene certainly seems to be enhanced in cold, and we can even begin to see that pollen may make a rather minuscule but still present amount of these genes. So there's some other still biological concerns, and I'm going to look at this gene first to demonstrate it. And what I'd like you to see is that even though all of these genes are set to the same scale, and I'll even make that a smaller scale, there is clearly an expression difference between the controls, even the two controls that are in the same experiment. Normally, what you would do is normalize that. You'd divide perhaps by the total number of single mapped reads for that sample, so that if you had a gene that was perhaps, if you had a sample that had 300 million reads and you had a sample that only had 30 million reads, you would want to normalize. And I will give you a sneak preview of the fact that we're putting in the ability to normalize these graphs in our next release. But I'm going to stick with the current release right now. Now, as we were seeing before, we seem to have in this gene, the 6.0 and the 7.5, differential expression based on temperature, which is usually what you're looking for, is that your treatment should have an effect. So once again, I'm going to run this back up to a larger number and begin to show you. Here, it's fairly evident to the eye that even though the matching control is lower than the other two controls, the cold is lower yet further. But it's a little difficult to compare them like this. So what I'm going to do is I'm going to join them into one graph. Now, I'm not going to use the pollen since the amount that is expressed in pollen is minuscule at best. So I'm going to click and then shift click to select those four. And I'm going to come down here in the graph tab and I'm going to choose join. And what it's going to do is it's going to assemble them into one line. Now, this in of itself may not seem to be that exciting in this state, but there's a number of different ways that you can represent a graph where this is useful. So for instance, I'm going to select heat map. Now, the default is a blue-yellow heat map, although there are many, many choices you can make. Here's a little more of a standard where no reading is red, some reading, a moderate reading is black, and a strong reading is green. And once again, it becomes immediately obvious that there are differences amongst these reads. Unfortunately, when you do this, you can't see the label. That is, of course, until you ask to have the label shown. And now you can see this is the cold track, and these are the three controls. And once again, you can readily see by this method that the cold is lower in expression here and higher in expression here. Another nice way to demonstrate this, still using the joined graph, is if we convert this to lines, and then either using the collapse tool or using the right click option to collapse, we can actually overlap the line graphs and have a very nice picture and representation of what's going on. This gene especially, you can see all of the controls overlap each other very nicely, and the cold very distinctly is higher, probably by 2 times, than the rest. On this one, it's not as clear. You have a lot of difference amongst the controls. However, it's still very apparent that the cold expression, which is the blue line, is still definitely lower than even the nearest control value. So I like using the join function to display stacked and overlapped graphs when I'm trying to make a particular point. Now I'm going to split these guys back apart, and when you split them, they come back in large, but they're all there and they're all present and they retain their name. So another thing, again, I'm going to switch them all back to the stair step because I find looking across them to be easier if they're solid. Again, whatever works for you is the right answer. I do want to point out that graphs are a great way to explore your data. This doesn't look like anything at the moment, and especially because there's no annotation here. But if I run this down to, let's say, 100, suddenly it becomes incredibly apparent that there are reads here. There's a significant number of reads here, and these gaps between chunks are very typical of introns. This is exactly what you would expect to see if there was a gene here. 3 exons, 2 introns, and yet there is no annotation. So graphs are a great way to explore and find new genes, or another great trick is to find genes where it doesn't quite match the annotation. For instance, right here, we see that there's the mass of reads that align to that portion of the annotation. Excuse me a moment. Okay, there's a massive gene of reads that align to that annotation. There's a massive reads that align to this exon. But here we see that the exon is only annotated out to this point, and yet the reads extend quite a distance in this direction. We give you in IGB the ability to float a graph for almost this reason. Floating disengages the graph from the lockdown section and allows you to click and drag it so that you can either overlap it with other graphs or overlap it onto the annotation like this. In which case you can actually align it to the annotation and make sure it does or does not match as you like. Here we can show exactly where the edges are and where the edges of the reads are. So for instance, if you look right in this region, you'll see, once again, and it helps to be floating, that the reads line up in this position, which is distinctly different than the actual annotated splice location. And again, we can sort of lower the graph on top of this to identify just how different it is from what is annotated and what's actually seen in the data. And to unfloat, you can, even if you've clicked off and worked with other things, it's a fairly simple matter to click. The thumb is what we call it, and unclick float, and once again, it will snap into position and lock down. So these are the types of things you might want to use graphs for. And a lot of times that can be just enough. But then there are times where you actually want to work with the numerical material. So for instance, if all of these controls were from the same experiment, rather than having all of these 3 graphs, let's say I'd like to have a graph that's sort of the average of all 3. So once again, I would select those 3, and I would come down here to the multi-graph. And as you can see, we have all of the sort of basic mathematical manipulations you'd like to do. And here I'm going to select mean and apply. And IGB will draw for me a mean graph, which is the mean of those 3. Once again, it is marked with the IGB track. If I wanted to keep this, I would select it and click the Save Graph button, at which point it offers to allow you to save it out as a bed graph, which is also called a wig graph, which once it's saved out, it's an independent file that can again be opened in any program that will let you see bed or wig graphs. But now that I've drawn my mean, which is right here, it tells you what it's the mean of. I no longer actually need to be looking at the other graphs. However, personally, I like to identify my newly created graphs with a different color so that I'm not lulled into thinking it's a different graph. So I'm going to select all. I'm going to reset them to the same height. I'm going to reset them to the same Y scale max. And now this track represents the mean of all of those controls. Well, that's nice, that's convenient, but what next? Well, now I am going to select mean first, and then I'm going to select cold second. And I'm going to ask for a difference. In other words, subtract the cold from the average and show me what that looks like. And that's what we have here. Now, remember, there's definitely less in the mean than there is in the cold, so IGB will draw for you the negative side as well as the positive side. And again, I would typically color this something different, something that shows different. Another really useful thing, it's nice to know what the difference is, but a lot of times you want to know the ratio. What's the fold difference? So in that case, once again, I'm going to select mean first, then I'm going to select cold, and I'm going to look for the ratio. And there it is. Now, what's nice to do with the ratio, I'm going to increase the size of it. What's really nice to do with a ratio to help you when you're questioning, well, what fold do I have, is set the y-axis scale and set it to your minimum fold value. So in other words, I only want to consider genes that have a 5-fold difference. So I've now set the max y to 5, and I can look at all of these ratios. And the only gene that really shows close to a 5-fold is this one and the unknown gene right next to it. Everything else is sort of down at 1, possibly at 2. But of course, you also want to get the ratio of cold to mean. So once again, I'm going to select, ratio is still selected, I hit apply, and after it draws out, again, I'm going to select it, make it a little taller, and this time I'm going to set it to 5 again. Now you can see that all of these three, that this gene and this gene are nearly a 5-fold difference right here, even though the actual difference track doesn't show that much. So you can actually do any of these sorts of manipulations with your graphs to try to highlight the data you're interested in. Additionally, any of the single graphs can have any of these mathematical transformations that you feel that you need. You can even enter your own power if you want to put it to the power of 3, 5, or 10.2. Whatever works and makes your data easier to analyze is the right answer. So that's the things you can do with graphs right now. And as I promised, I was also going to show you this. So once again, what I have, this is that same region we were looking at, and this is a different experiment where we're using a control and a heat treated. Now, if you just look at the graphs, you can see I set them to exactly the same scale. And yet, even on the same scale, every single gene, the hot track shows cooler. But there's a reason for that. It turns out that in the cool control read, right here, there was 29 million reads, but in the heat-treated track, there was only 6 million reads. So that scale of difference is the time that you really need to be able to normalize. So I'm going to normalize, and just because I want to be able to keep the y-axis scale convenient, I'm going to set these numbers to a convenient decimal. And I'm going to take the number of single mapping reads, and I'm going to take this graph, and I'm going to ask it to, you can see right here, the single graph base, and we've added in add, copy, divide, and subtract is in there as well. I'm going to divide by my number. And this is going to normalize that graph. So once again, I'm going to go hide the original because I don't need to see it, but I'm going to keep the normalized graph. I'm going to come back and do the same thing here, except I have to, where did I just lose that? There we are. I'm going to divide by the number of single mapping reads in that sample. Come on. This is our working copy, so occasionally bugs creep into this copy. This is how we test and fix our new features. There. Alrighty. So again, I'm going to hide the original track. And now you can see these are both set essentially to the same scale, although I can ensure that. And now at the same scale, looking across this data, it becomes very much more apparent that these are all roughly expressed at the same value all the way across. It might be that at this position that the cool has more, but again, this is now set on a normalized scale, and we can reasonably and scientifically compare these samples. So thank you for joining us. I'm going to stop the recording now and open up the floor to questions. Thank you.